Hi everyone, I'm Tegan Brennan, a PhD candidate from the University of California, Santa Barbara. Today I'll be presenting my work with Shamanta Saha and Tefik Bolton on JVM fuzzing for side channel detection. In general, side channel vulnerabilities in software are caused by observable differences across program paths. Consider the equals function shown here, which compares a guess and a stored password character by character. As soon as a mismatch is detected, this function returns early. This introduces a side channel in time, allowing some observer to determine how many characters of the guess match that of the stored password. We can experimentally examine this side channel. To the right, I showed the results of two different experiments. The violin plot in blue shows the execution time behavior of this equals function when the first character of the guess does not match that of the stored password. The violin plot in green shows the execution time behavior of the function when the first two characters do match. These execution time distributions are distinguishable, illustrating the side channel we hypothesized about. This side channel is caused by the early return in the previous function. So to fix it, one might think, well, let's remove the early return and instead ensure that the same amount of work is done regardless of whether or not the two characters match. As a result, a developer might code the equal function here on the left. So, has the side channel been removed? To the right, I show the results of the same experiment on this new version of the equals function. Now, these execution time distributions appear to be indistinguishable. Looks like the problem is solved, right? Well, one crucial bit of information is that this experiment was run with just-in-time compilation disabled. When I run the same experiment enabling JIT, the story has completely changed and a side channel has arisen. This side channel is due to just-in-time compilation. As JIT attempts to optimize paths it deems hot, it can introduce timing side channels even into code that appears to be balanced at the source code level. These side channels are due to an imbalance in the input distribution of the program, leading the runtime to favor certain program behaviors. In our work, we focus on the automated induction and evaluation of JIT-based side channels. To automatically induce JIT-based side channels, we attempt to fuzz the runtime into as many different states as possible. Then, we evaluate each runtime state for side channel vulnerabilities. Our technique requires a strategy for finding different runtime states, as well as a way to evaluate the vulnerability of each state. We present a two-phase approach. The first phase is an input generation phase, and our first goal is to generate priming input. Priming input is program input that is repeatedly sent to the runtime, priming it to favor certain program behaviors. We generate priming input via the fuzzer AFL through the interface Kalinchi. We use AFL in order to cover many program behaviors. Even though AFL does not guarantee coverage of all program paths, we still empirically found it to be effective at generating input executing different program behaviors. The second goal of the input generation phase is the generation of pairs of evaluating input. If the pairs of evaluating input are separable through their execution time behavior, then there is a side channel in the primed runtime. In generating evaluating input, we want to find partitions of the input space that are most likely to be separable. Returning to our motivating example, we gain the intuition that these are partitions that differ on some secret dependent branch. To find evaluating input, we begin by using dependency analysis to mark all secret dependent conditionals. To the right, I show the program Sanity Safe from the Blazor benchmark. Sanity Safe takes two input, and one, the integer a, is marked as secret. After dependency analysis, we create an instrumented version of the program under test. For any branch condition, this instrumented version keeps track of an integer, which is set to 1 if the branch is taken, and left as 0 otherwise. Similarly, a counter is introduced for every loop, which is incremented for every loop iteration. In the end, a tuple is produced that defines the behavior of the program at branches and loops for any given input. Using this instrumented version of the program, we produce input tuple pairs. We then match the tuple to predefined patterns and use this to partition the input into evaluating sets. At a high level, our patterns try to find two sets of input that disagree on a secret-dependent conditional, but agree as much as possible elsewhere. Once we have generated priming input and evaluating input, we turn to systematically fuzzing the runtime. We prime the runtime in favor of each priming input in turn, and then determine if that particular runtime state is vulnerable to a timing side channel. We evaluate this by determining whether the pairs of evaluating input are separable via their execution time behavior. We evaluate our approach on the Blazor, Themis, and difffuzz datasets widely used for side channel analysis. Each of these datasets consists of two kinds of programs: the original programs containing a side channel vulnerability and their fixed, safe counterparts. We experimented on both sets of programs, but I show our results on the safe variants here. Our automated approach was able to induce JIT-based side channels in the majority of these programs. In the Blazor dataset, we are able to induce JIT-based side channels in 13 of the 14 supposedly safe programs, contradicting the results of 4 state-of-the-art tools for side channel detection. In the end, we think our results demonstrate the need for side channel analysis techniques to consider the dynamic behavior of the runtime. Without this consideration, potential side channel vulnerabilities may be overlooked and programs may be mistakenly considered secure. We think our automated technique bridges this gap in the detection of JIT-based side channels. Thank you for coming to our presentation, and please reach out with any questions.